Sure. So welcome back, guys. I hope you had a great long weekend. What did you guys think about the quiz last week? Quite enjoyable, interesting. Um, so I've set the quiz that your marks will be available now, and I've also set the quiz that the correct answers will also be available now. So the questions in the quiz, that's the questions you can expect for the semester test and exam as well. Yes, go ahead and ask your question, Mr. Levuyo.
Hello, sir. So my question is about the naming of the constellations. Um,
Yes.
so in the book, if I'm not mistaken, it says that it's Greek translated into Latin, right?
Yes.
But then what was the answer in then does that not mean that the stars are Greek, like a Greek sort of like a Greek named?
Okay, so I see what you're meaning. So uh, let's go through the memo of the test, and then I think that will clarify everything. So let's start. So I randomized the questions for you guys. So just to make sure that copying was eliminated a little bit. So the first question on my side was the average distance from Venus to the Sun is um, 1.2 light. Let me rather do this. Should I share my screen with you guys? Okay, so let me share my screen. Can everyone see my screen? Okay, cool. So the first question I had for you guys is the average distance from Venus to the Sun is, and my eyes zoom in. So let me see if I can zoom in. Is this better? Okay, so first question is the average distance from Venus to the Sun is 1.2 light years, 0.72 AU, 1.3 million kilometers, 1 billion kilometers, 2,3 miles. So why would the answer B be correct? Unit of measure, but let's discuss this a little bit. So yes, so that is correct. Venus is closer to the Sun than Earth is. That's a key point to remember. So remember, distance from, yes, let's say Mr. Groenewald, because 1 AU is the distance from the Sun to the Earth, and Venus is between the Sun and the Earth. Yes, that's very important. So now, let's look at option number A, 1.2 light years. So remember, light travels at 300,000 kilometers per second. So converting that into light years, that's a hell of a distance. So if you think about it, that's the light that That's the distance light travels in 1 year. So 1.2 light years is a quarter to the way to our closest star. So that's not going to work. So option B, so we know the distance from the Sun to the Earth is 1 AU. 1 AU is 150 million kilometers. So that could be correct. Then we go to number C, 1.3 million kilometers. 1.3 million kilometers is a bit short. Remember, our distance from the Earth to the Sun is 380,000 kilometers. So that's basically the distance is basically the distance to the moon times 4. So imagine the moon being 4 times further away. So that's not going to work. So let's go to D, 1 billion kilometers. Thinking 1 AU, so 150 million kilometers. So 1 billion kilometers is way too far. That will be more or less in a range of Jupiter. Then we go to E, 2.3 million miles. Again, that's again too far. That's outside Earth's orbit. So the only one that makes sense is B. And when we do the calculation or Google it, then you will see it's 0.2 AUs. How much is 0.72 AUs in kilometers? Anyone has an idea? Yes. So you're all happy with question number 1? Okay, then question number 2. Our Milky Way galaxy has a diameter of 75,000 light years. How long does it take light to cross the diameter of the galaxy? So does anyone want to volunteer on this question? So the easiest way to think about it, a light year is how far light travels in 1 year. So the time will be 1 year. So 1 light year will be 1 year. 2 light years, 2 years. So let's think about the closest star to Earth, Alpha Centauri. That's more or less 4.2 light years away from us. So it will take us 4.2 years to reach it. So we have a diameter of 75,000 light years. So that means it will take 75,000 years. Everyone happy with that? Okay, then question number 3. Remember last week we did an example of this, if you remember correctly. So the apparent visual magnitude of a star is 7.3. This tells us what? So remember our eyes maximum is apparent visual magnitude of 6. So A, one of the brightest stars in the sky, that's not true because we know Sirius and a few other stars is at -3. So B, bright enough to be visible during the day? No. C, not visible with the unaided eye. D, very far from Earth. E, very close to Earth. So distance and apparent visual magnitude, we will learn later, does not correlate. So the only option remaining is not visible with the unaided eye. Happiness? Okay, then question number 4. Star A has an apparent visual magnitude of 15.4 and star B has an apparent visual magnitude of 12.4. So star A is what, then star B? Any volunteers how we would solve this problem or do this simple equation? Any volunteers? Why is everybody so quiet this evening?
So is the equation not uh it has something, okay, so it has something, it's I think it's 2.51 to the
Yes.
power of the magnitude of star B and minus the magnitude of A. And then on the
Yes.
equal side, that's what I'm not sure of. I kind of forgot what it is.
Okay, so let me quickly open up the equation for you guys.
Oh, I remember. It's the flux of B divided by, oh, the flux of A divided by the flux of B. Yes.
Yes. So let me quickly just find our lecture slides, find the equation where we did it, and that will help us. Now that is the one thing, if you have too many tabs open at the same time, you get confused where everything is. So I'm just going quickly running through the slides. Okay, got it. So page 6 in textbook, F over FB. Yes, so you all remember this equation right here. FA over FB equals 2.51 times MB minus M0 to the power MB minus M0, right? So how would we use this equation?
Hi there. So, am I allowed to just freely speak?
Yes, go ahead.
All right, perfect. So basically, all we need to do really is just use that formula, the right-hand part of it. So we say 2.51 with the remainder of the well, it's generally just a given variable. So we'll often just use that, and then we'll put it to the power of the difference between the two magnitudes of brightness, and then we come to the answer of 16. If I'm correct.
Yes, that's exactly correct. So with this, there is just one other thing I would like to ask you guys. So in this, we can see there's two options that can be correct. 16 times fainter, 16 times brighter. So how do we know if it's fainter or brighter?
Well, so the larger the value, the fainter the brightness, if I can say that.
Yes, that's exactly it. So are you guys happy with this explanation? And this is about the hardest calculation we will do in this course. So the rest of the calculations we will do will build up on this, but this will be basically our hardest calculation. And then the last one that most people got wrong is star names are Latin, Greek, Arabic, English, Italian. So I also discussed this in our lecture slides and went through the lecture. I think this was in our opening lecture as well. And those of you that are fans of Neil deGrasse Tyson, he has spoken about this also quite a few times. So, when astronomy began, contrary to belief, most of the scientific work in the world happened in the Middle East up until the Middle Ages. So if you look at star names, 70% of star names is from a Middle Eastern origin, so Arabic. If you look at constellations, that's where your Greek and Roman philosophers come into the picture. They usually named constellations Latin, and the Latin was translated into Greek and in Roman as well. That is why when we speak to constellations, depending on what gods they was important during that time, such as Zeus, Apollo, and other mythical creatures, the constellations will either have Greek names or Roman names. But 70% of all stars has Arabic names. You guys happy with it? Okay, cool. So next week's lecture, I will give you a bit of statistics on how the class test went. So I'm just going to close this down and stop sharing the screen. So with this questions, luckily these quizzes don't tell a lot for your final mark. So these quizzes are to help you guys to show how I ask questions. And it's also an indicator to me of where you guys are struggling with the work. So no, there won't be a quiz this week. I will let you guys know when we will have the next quiz. I haven't checked it yet. I will send out notification on ClickUp and also the WhatsApp group and Discord tomorrow when the semester test will be. So a bit off topic, but I want to show you guys something cool. So I'm going to just turn on my camera. So you guys will all see me now. So I just want to show you the cool cell phone cover my girlfriend got me. This is full of math equations. And then there's a different one full of physics equations that I thought that was actually really, really cool. I have no idea where she got it, but that is pretty cool. So before continuing with tonight's lecture, I'm going to ask you guys, have you guys got to hit us all up at the end of this module? If you guys are interested in, I can find out how and where these covers can be available. But before we continue, awesome. So before we continue with tonight's lecture, I want to ask you guys something interesting you have learned or heard or read in science the last week. Yes. Ingenuity. So if you haven't joined the WhatsApp group yet, just please send me an email with all your details. So sir, lecture free slides isn't available on ClickUp. I will make sure all slides uploaded or visible. It could be that visibility is for some reason set to not accessible. What is this link you sent, Mr. Els? Let me open it up quickly and see what it's about. Oh yes, NASA's InSight land detects 2 medium Mars quakes on the red planet. I saw that as well, so that is pretty cool. They recently changed the kilogram. I've read that as well. Apparently Uranus is leaking radiation. That is also true. Uranus, Jupiter, and Saturn is radiating a little bit of their own energy, but we will discuss that in this module specifically. They are planning the route for the first helicopter flight on Mars. And I also have seen they are planning a new accelerator at CERN. And yes, the new polarized magnetic lines from the original EHT image, that is also astonishing work. So in your third year and in honors, you will come across Professor Roger Dean, and he is working on the EHT imaging. So for tonight's lecture, we are going to discuss a little bit more about telescopes. What's the basic components of a telescope? What's the difference between an optical telescope, radio telescope, the basic equipment on both of them, how both of them operate? What are the different windows we can look at? So speaking of windows, different frequencies, wavelengths, images we can get through our telescopes, and from different observatories and observational instruments and techniques. Before we start, do you guys have any questions on last week's work? Anything you want to know? Anything I can help with? So just an announcement from my side. Yesterday I've received an email from the faculty and also a WhatsApp from our HOD. All contact and face-to-face lectures, contact time on campus has been suspended. There are currently 115 students that have tested positive for COVID-19. So right now the university has decided to suspend all face-to-face activities but that will resume in the future again once we know that the students that tested positive is all good and well and no one else was infected. So that is actually a very good question. So last year, um, all lecturers and people um, had to submit we call it a redundancy teaching plan. So what would happen if we move up and down in the COVID levels? So the idea was on level 1 that we have a phased approach to letting students back on campus. According to regulations, we are allowed to have 70% of students back on campus. So we're busy with the phased process of getting everyone back. But because there are now 115 positive cases on campus, campus has moved up to level 3 restrictions. So no one is allowed on campus until we see this problem solved. Then we will go back to phase 1 and letting students back on campus again. So that is a bit of a problem. So if there were no positive cases on campus, then more people would be available to come to campus. Also, on a different note, I will let you know when we are back on level 1 at campus. With level 1, if you would like a face-to-face consultation time, that's easy to arrange. Just send me an email, but because we're now on level 3 restrictions at campus, the best I can do is a video call through any platform. So if we have not been conveyed this information from another module, we just planned for contact sessions this week, do we assume all contact is restricted? So the email, so let me read the email I've received. I would suggest just to email that lecturer and make sure. But the email I've received said, dear staff and postgraduate students, contact teaching at UP has been suspended on the Hatfield campus, and there will be implications for postgraduate and possibly postdoctoral access. So this is the question here. So the email sent out from the executive to the deans was, you are undoubtedly aware of the outbreak of COVID-19 cases at the University of Pretoria, with 115 students testing positive for the virus in the most recent count. Consequently, the university executive yesterday decided that as from 6 April 2021 and until further notice, all contact instruction will be suspended at UP at all campuses, with the exception of the Onderstepoort and Prinsenhof campuses. Only essential contact activities at the latter two campuses will be permitted for veterinary sciences and health sciences students, and with the strictest health and safety protocols being observed. The executive also urges all faculties to immediately reduce all contact meetings on all campuses and to ensure that all health and safety control measures are strictly observed at all time. I hope that you will appreciate the urgent need for the implementation of the above-mentioned measures, given current conditions. Consequently, please make every effort to inform all of your staff as soon as possible of the two above-mentioned decisions. And that's the email I received. I have no idea. So with this, I would suggest if you had any contact classes scheduled, just to email your lecturer and ask what is going on. So starting tonight's lecture, I would like to open up with the following quote. The strongest thing that's given us to see with a telescope. Someone in every town seems to me owns it to the town to keep one. Telescopes gather and focus light, so you need to study what light is and how it behaves. On your way to understanding how telescopes work, you will learn about telescopes that capture invisible types of light, such as radio waves and X-rays, enabling astronomers to put together a more complete view of celestial objects. So in this chapter, we will be looking and discussing at what is light, how do telescopes work, what are the powers and limitations of telescopes, what kind of instrument do astronomers use to record and analyze light gathered by telescopes, and why must some telescopes be located in space? The science of astronomy is based on observations. Astronomers cannot visit distant galaxies and far-off worlds, so they have to study them using telescopes. The quest of astronomers is to study light from the Sun, planets, moons, asteroids, comets, stars, nebulae, and galaxies and extract information about their natures. Most celestial objects are very faint sources of light, so large telescopes are built to collect the greatest amount of light possible. Some types of telescopes gather light that is invisible to the human eye, but all telescopes work by the same basic principles. Some telescopes are used on Earth's surface, but others must go high in Earth's atmosphere or even above the atmosphere into space to work properly. This chapter focuses on telescopes, instruments, and techniques used to analyze light for astronomical research. Astronomers no longer spend their time mapping constellations or charting phases of the moon. Modern astronomers analyze light using sophisticated instruments and techniques to investigate the composition, motions, internal processes, and evolution of celestial objects. To understand how astronomers gain such detailed information about distant objects, you first need to learn about the nature of light. When you admire the colors of a rainbow, you are seeing an effect of light acting as a wave when you use a picture of the same rainbow. The light acts like particles as it hits the camera's detectors. Light has both wave-like and particle-like properties, and how it behaves depends partially on how you treat it. So I'm sure you guys have all heard about a concept that light is both a wave and a particle. So everybody is comfortable with this idea, and I don't have to, you want me to explain it better, or are you guys happy with it? Awesome. So before continuing on, just a bit off topic, I usually ask this my class just to see where your interests is. So generally in science, what do you find most interesting or intriguing? Inside of atoms, waves and computing. So just here, quick thing, astrology. We're not doing astrology in this course. Astrology is looking at star signs and making up hocus pocus. The correct term is astronomy. So motion, astronomy. So if you ever guys thought about this a little bit further, so if you look about quantum mechanics, then you can start looking at particle physics. In astronomy, you can break it down into astrophysics, cosmology, thermonuclear astrophysics, instrumentation. Then there's the human mind. There are planetary science, atmospheric science. Just another question, just to get my feelers out. Do all of you have physics as a first year course? Dark matter and dark energy? Good. Okay. And I assume most of you had physics in high school. Okay, cool. So there's a few yes and no's. Um, that is good to know. So to get to the explanation of waves and particles, so light is referred to as the electromagnetic radiation because it is made of both electric and magnetic fields. The word light is commonly used to refer to electromagnetic radiation that humans can see. But visible light is only among many types of electromagnetic radiation that include X-rays and radio waves. So in this figure is the electromagnetic spectrum. So from the electromagnetic spectrum, we know that wavelength and frequency is inversely proportional. So the larger the wavelength, what will happen to the frequency? Yes, lower the frequency. So yes, so the smaller the frequency we have, yes, exactly. So here we can basically see if we have something at, let's say, 10 hertz, our wavelength would be 10 to the power 7 meters. Going the other way around to gamma rays, here we have the frequency as 10 to the power 24, and our wavelength will be 10 to the power minus 16. So in this electromagnetic spectrum, we have long radio waves, we have AM, FM, microwave, IR is infrared, visible light, we have UV, we have X-rays, we have gamma rays. Looking into our visible light spectrum, there we have our wavelength. So bluish light is at 400 nanometers, reddish light is at 700 nanometers, with anything in between, and that correlates again to a specific frequency. Are you guys comfortable with the electromagnetic spectrum? Okay, cool. Just something to remember that will lead up to astronomy and what we can detect and observe in astronomy. If we have a, yes, Mr. Lavuyo.
So my question is, how do we know that how long these electromagnetic waves are?
Okay, that's a very good question. So how do we know how long these electromagnetic waves are? The best answer is we can actually physically measure it. So somewhere in your careers, for all the physics students, you will do a course on electromagnetism somewhere. So usually, traditionally, the electromagnetics course is usually considered as the most difficult physics course, just because we cannot see electromagnetic waves with our eyes visually. So the best way to interpret electromagnetic waves is by using math. And the math for electromagnetism can become extremely hectic very fast. But a rule of thumb is with electromagnetism and radio, so magnetic waves and um, the magnetic fields, electric fields is the correct term I'm looking for, is you can physically measure them. So usually the rule of thumb is if you want to measure the wavelength of a certain signal or a certain part of the electromagnetic spectrum, your antenna needs to be a quarter of the size of the physical wave. So let me get out the whiteboard. This will help you a little bit. So this is just a little bit, you don't have to know this for this course, but this is something interesting. If we have our, this is our x-axis, this is our y-axis, and we draw just a normal sinusoidal wave on this. This is one period. If you guys are, do you guys agree with me? So if you look at this, what is the smallest piece of the sinusoidal wave we need to reconstruct the rest of the wave? One times the period, or you can go smaller than that. So we can even, half will work, but we can do better. Yes, a quarter. So if we divide this into, say, different parts, different quarters, we say this is quarter 1, quarter 2, quarter 3, quarter 4. So if we have only any one of these segments, we can reconstruct the original signal, true? Do you guys agree with me? Okay, cool. So ideally, when you want all data of a signal from the electromagnetic spectrum we want to observe or want to detect or want to measure. Our antenna has to be exactly the size as one wavelength, so meaning one period of the signal. So this would be one period. But we know with math, we can divide this into quarters. That's the smallest piece. And if we have one of these quarters, we can use that one quarter to figure out where it is on our sinusoidal graph. So say, for example, we have quarter 2, then we know, okay, this is the maximum amplitude we have. So that means we can reconstruct quarters 1, 3, and 4. If we have, for example, quarter 4, we know how to reconstruct quarter 3, 2, and 1. So by making use of our antennas, that means we don't need an antenna that is physically the size of one wavelength for one period, but we only need a quarter of the antenna has to be the quarter of the wavelength. That means we can reconstruct the wave. Does everyone understand that? Yes, Mr. Lavuyo.
So when you collect data, is that quarter of a wavelength like a picture, and that's why we don't take videos of the sky?
Interesting question. I will explain that now as well. So just before I forget, I saw here a comment, are we doing Schrödinger's equation? Unfortunately, not in this module. You will do that in your quantum mechanics and also in statistics. So when we have this, so everyone understand we can reconstruct our wavelengths. So let's go back to our slides. Where's that slide now? So that means if we look at long radio waves, that's right about here. If we want to detect a radio wave that has a wavelength of 1 meter, what is the ideal antenna size that we want to detect it? Okay, so that's the minimum, but what is the ideal size? The ideal size, yes, will be 1 meter. So the exact same wavelength we are picking up, but because that becomes a problem, we can get away by using an antenna that is 0.25 meters or a quarter of the wavelength to detect our signal. So let's do a little bit of a mind example to explain where this is. Yes, this applies to all wavelengths. So let's go, for example, I want you guys to, if you can just, let's do the calculations. So let's say we want to detect a frequency of so this is how we would want to communicate. So yes, so the full explanation will explain everything. So if we want to detect a signal that the wavelength is 100 meters, so 100, what will be our ideal antenna size? Yes, and what is the smallest size antenna we can get away with? Yes, that is 25 meters, exactly. So let's go a little bit to the other side. So let's talk about our cell phones. So where do you think is the, not a wavelength, the frequency of our cell phones? So to make a cell phone call, send a WhatsApp message, your normal cell phone. Yes, that's correct. So 10 to the power 10 hertz. That's correct. So we are looking at between 90 megahertz all the way, not 90 megahertz, 90 gigahertz all the way up to 110 gigahertz. So let me get our whiteboard out again. This will make it a little bit easier. So you all are probably familiar with this equation. Lambda equals C over F, where this is our wavelength, this is our frequency, and this is our speed of light, right? Are you guys familiar with this equation? Okay. So now I'm going to ask you to do this little equation for me using this formula. So let's say we have a wavelength of 1 kilometer. What frequency will that give us? Yes, that's exactly it. So from this, we can see we have a very, very large, not that we have a large frequency, right? So from this, I quickly did the calculation myself. If we do the equation, we swap it around. We have frequency equals C over lambda. Correct? Do you guys agree with me? So we want the frequency of 100 meters. So you know the speed of light is 3 times 10 to the power 8 over 100 meters. So this will give us a frequency of 3 meters. So this will give us 3 megahertz, right? Do you guys agree with this? Okay, so let's go to the far opposite spectrum, and we do this calculation again. So 3 times 10 to the 8, and we make this a, yes, mega. So let's make this 1 kilometer. That would be, and that would be 3 kilohertz, right? So now coming back to our cell phone signals, yes, 300 kilohertz. So do you guys know what frequency our cell phones are operating at? That is correct. Okay, so what is the difference between mega and kilo? So let's do let's do this. So kilo is 1,000. So kilo equals 10 to the power 3. Mega is 1,000,000, so that's 10 to the power 6. Giga is 10 to the power 9. In tera, 10 to the power 12. You are correct. So when we are looking at our cell phones, what size do you think our antenna needs to be? So if we look at our normal 4G, or another word for this, LTE cell phones, they operate at a frequency of what would you guys say? That's also something I'm going to explain to you guys next, where this is all leading up to. Yes, that's exactly it. So for 4G, that is 750, that's horrible, megahertz, to, depending on our operator, 2,500 megahertz. So if we take our normal equation, C over F, and we want our wavelength. So we have C, 3 times 10 to the power 8. And let's take the larger of the two, say 2500 megahertz. What will our wavelength be? That will be, yes, 0.12 meters, and that will be 12 centimeters. So how big are your cell phone, guys? How many centimeters tall will you guess your cell phone, and how many centimeters is the width of your cell phone? So that means for our 4G or LTE signal, our antenna ideally needs to be 12 centimeters. But we can get away with a quarter of that. So a quarter of 12 centimeters is 3 centimeters. So when you open up your cell phone and you look at your physical size of your antenna, that would be between 3 and 5 centimeters. So that is why cell phone signals are chosen to operate at such high frequencies, so we can get our antenna as small as possible to detect those signals. So it wouldn't be nice if you had a cell phone but you had to carry around an antenna that's a meter long. So to pick up cell phone signals, our antenna in our cell phones needs to be between 3 and 5 centimeters. So, question, when doing these calculations, how should we know, how should we leave our answers? Because some are in centi, megahertz, kilohertz. So we always leave our answers in SI units. So in SI units, depending on what we're using for, is usually meters. So if we have something that is something like 300,000, say 300,000 hertz, it makes it easier to write this as 300 kilohertz, if that makes sense. So question, in this case, wouldn't we take the average of these two frequencies, or am I wrong? So let's do the calculation for the other way. So if you want to do the wavelength, and we have 3 times 10 to the power 8, and we do it the other way around, and we have 750 megahertz. This will give us 0.4 meters. And that will equate to 40 centimeters. So we need a quarter of the wavelength. So that means we will need an antenna that is 10 centimeters long. So cell phone designers pick the size of the antenna to pick up all these frequencies. So here we know we need for this one, for the large, we need more or less an antenna 4 centimeters. Yes, Mr. Lavuyo.
So what's better? A frequency that is shorter or a frequency that is longer?
Good question, Mr. Lavuyo. So it all depends on your application. So from theory, we know ideally to pick up the correct signal, the ideal antenna needs to be the exact size of one wavelength, but we can get away with antenna that is quarter the wavelength. So ideally, always best case scenario, we want an antenna that is as long as the wavelength or even bigger. We'll say, for example, we want to pick up a 1 meter wavelength. Best case, we want an antenna that's exactly the same, that's 1 meter. But if we have an antenna that's any size bigger than 1 meter, we will still be able to pick up the 1 meter wavelength. Smallest will be a quarter of the wavelength. So now coming back to our slides, let me just get the correct slide. Yes, Mr. Lavuyo.
So if you require, so what happens if so what happens to these other wavelengths that don't necessarily interact with the telescope? Do they just fly through it, or do they
So
get
that
bounced
depends
around?
on, so yes, that's exactly what happens. If let's say for example, you have a telescope that's 1 meter in diameter, and we want to look at signals that is, so for example, 50 meters in diameter. That means our telescope is too small to see that bigger signal. So usually that's why we want a telescope that's as big as possible to cover most of the wavelengths. So when we look at our electromagnetic band we have, now we know how the size matters. So if we want to build a telescope to pick up long radio waves, that means we're going to need one hell of a big telescope to have 1/4 wavelength. But going to X-rays and gamma rays, if we want to pick up or observe them, we can get away with a much, much smaller telescope. And the same principle is with visible light as well. So you guys happy with this explanation, this exercise we did? Awesome. So just something interesting. If you have an old analog radio or an old analog TV and you want to make a makeshift antenna, your antenna needs to be, you can take just a piece of normal wire. It just has to be a meter long and you will have an antenna that's able to pick up FM. So, some people are wary of the word radiation, but that involves a common misconception. Radiation refers to anything that radiates from a source. Dangerous high-energy particles emit from radioactive atoms are also called radiation. And you have learned to be concerned when you hear that word. But light, like all electromagnetic radiation, spreads outward from its origin. So you correctly refer to light as a form of radiation. Electromagnetic radiation travels through space at a speed of light, so 3 times 10 to the power 8 meters per second, symbolized by the letter c. This is commonly referred to as the speed of light, but is in fact the speed of all types of electromagnetic radiation. Yes, that's true, alpha, beta, and gamma radiation. Electromagnetic radiation can act as a wave phenomena. This is, it's associated with a periodically repeating disturbance, a wave which carries energy. Imagine placing a ruler parallel to the travel direction of the wave. The distance between peaks of the wave is called the wavelength, usually represented by the Greek lowercase letter lambda. Wavelength is related to frequency, the number of waves that pass a stationary point in 1 second. So frequency is often represented by the Greek lowercase nu. On the moon, where there is no air, there can be no sound. In contrast, light is made up of electric and magnetic fields that can travel through empty space. In other words, unlike sound, light does not require a medium and can travel through a perfect vacuum. Although electromagnetic radiation can behave as a wave, it can also behave as a stream of particles. A particle of electromagnetic radiation is called a photon. So you guys are all familiar with photons. Awesome. So you can think of a photon as a packet of waves. The amount of energy a photon carries is inversely proportional to its wavelength. Notice in the equation that there is a relationship between the energy E of a photon, which is a particle property of light, and a wavelength lambda, which is a wave property. The inverse proportion means that as lambda gets smaller, E gets larger. The shorter wavelength photons carry more energy, and longer wavelength photons carries less energy. That is why you think about it as radio waves has less energy than X-rays. So now, when we look at Earth's atmosphere and the electromagnetic spectrum, because remember, certain particles in our atmosphere absorb certain frequencies, certain particles in our atmosphere reflects certain frequencies. So here we can see we have two windows looking through our atmosphere. The one is our radio wave window, so radio waves penetrate the atmosphere quite easily, and visible light penetrates the atmosphere quite easily. And we struggle with microwaves, infrared, X-rays, and gamma rays. So when does light behave like a particle and when like a wave? It acts as both at the exact same time. It all depends on our application of what we want to do. Yes, sir, go ahead.
Say, what about in a vacuum? Does light also act as a particle in a vacuum?
Good question. So yes, if we have an electromagnetic wave such as light in a vacuum, it still has a wave principle and still have a particle principle. So in a vacuum, it can still be a particle and a wave. If we look at sound, in sound, we need a medium for sound to travel through. So that's why if you look at sound, we need our air around us, proper ground. We need solid material such as ground. We need water. But in a vacuum, we don't have any sound. Does that answer your question? Okay, so why is the sky blue? Coming to that now, just before you know, So in sci-fi movies, when you have your spaceships going through space, think about Star Wars, think about Star Trek, you have your lasers making all those fancy sounds and the engines making sounds. But in reality, when you're traveling in space, there won't be any sound outside the ship because there's no medium for the sound wave to propagate through. If you guys have ever thought about that. Then also, even watching sci-fi movies, especially in Star Wars, when you see your nice X-Wing fighter or TIE fighter doing all those fancy maneuvers in space. In real life, that's also not possible because you need air resistance to bank left and right. So that maneuvers is not possible, but Hollywood thinks differently. So questions are basically sound needs a surface to bounce off. Almost. So sound needs air to propagate through some sort of matter. It can be solid matter, such as our brick houses, the grounds beneath us. Air is also matter. Water is also matter. So it needs a medium to travel through. So no medium, no sound. So that's why there's no sound in a vacuum. So if you scream in space, can you hear yourself? No, you can't. Because as soon as the sound waves leave your mouth, you have no medium for them to propagate through and you won't hear anything. So that's why there's this joke going around in space, no one can hear you scream. So another question, why the sky is blue? That's also something we're going to discuss in this course, but in particle physics, that forms part of a principle called the Rayleigh scattering principle. So when we look at the atmosphere, because we have different wavelengths of light, so when we look at this, blue has a shorter wavelength and reddish colors has a longer wavelength. So with our atmosphere, blue light gets scattered into the atmosphere. So let me get the whiteboard out. Let me get another color rather. Not to confuse anything. If this is the atmosphere and we have our incoming light waves, blue waves will scatter across the atmosphere and more reddish light will penetrate the atmosphere better. And that's why the sky is blue, because we see the scattering of the blue light. So let's see a few of the questions. Can you say humans are radioactive since we produce and emit heat? Although not a lot. Yes, you can say that. Anything that's radiate energy even radiates energy is radioactive. You could put it crudely that way. So yes, Mr. Eckhart, that's exactly it. The sound pushes through air and the air vibrates against the eardrum. Yes. So yeah, why all spaceships in space, such as Star Wars, are always facing the same gravitational direction, if that makes sense. Yes. So how are spaceships propelled in space? Because it's like a vacuum. I highly doubt action, reaction take place in a vacuum. So yes, that's exactly how a spaceship is propelled in a vacuum. So we have for every action we have an opposite and equal reaction. So what's happening in space, you have your engines, and that has the flames and thrust gases coming out at the back, but that has the same. So let me do this. I like this whiteboard app. So this is our rocket. Here we have our rocket going off. And then from this also we have gases and plumes coming out. So with these gases and plumes coming out, they are traveling this way, but it has an opposite and equal reaction, pushing the rocket that way. And that is how propulsion works in space, the sweet and short of it. So is there a limit to how big and how small we can build our telescopes? Yes, that is exactly why I did this exercise, to show the size of the antenna we need is exactly to address that point. So the average wavelength of, so this implies that Newton's third law works in a vacuum? Yes, it does. So the average wavelength of visible light is about 0.005 millimeters, so roughly 50 light waves fit end to end across the thickness of a sheet of household plastic wrap. Scientists usually give the wavelength of light using nanometers units, equal to 1/1000th of a meter. Another unit that astronomers commonly use is called an angstrom, named after the Swedish astronomer Anders Jonas Ångström. 1 angstrom is 10 to the power minus 10th of a meter, so 1/10th of a nanometer. The wavelength of visible light ranges from about 400 to 700 nanometers, so 4,000 to 7,000 angstrom. Only visible light, some shorter wavelength infrared, and some radio waves reach Earth's surface through wavelengths called atmospheric windows. Obviously, if you wish to study the universe from Earth's surface, you have to look through one of those windows. So if we go back a slide, these two are our atmospheric windows, our visual window and radio window. So, but how do we know the bigger wavelengths don't exist? We can do that by doing the math. So astronomers build telescopes to collect light for analysis from distant faint objects. This requires very large telescopes plus careful optical and mechanical engineering work. You can understand these ideas more completely by learning about two types of telescopes and their relative advantages and disadvantages. Light can be focused into an image in one of two ways. Either the lens refracts or bends the light passing through, or a mirror reflects, bounces the light off its surface. So, before going on to the next slide, explain these principles better. What is the most important components of a telescope. So let's see how big of class participation we can get with this discussion. Yes, we need a mirror. What else do we need? We use a mirror, lens. What else? Electronic components. Yes, we need electronic components, but that is becoming a little bit too fancy. So if we look at the basic things we need for a telescope, what do we need? We can sum it in 3 components. So we have 1, that's that's horrible, that's written, lens or a mirror. 2, we need some way to focus it. And then 3, yes, Mr. Richard, bingo, the stand. And then there's one other thing we can add, and that's our detector or recording device. Yes, so the eye is viewing it, our CCD camera taking a picture of it, our spectrometer getting a spectrum of something. It could be any one of those 3 things. Something quite interesting, when you buy a telescope, you will be surprised that your stand can sometimes be cost twice as much as your telescope itself, because the stand is a very important component. Because the stand needs to be as stable as possible, and those of you that have telescopes, see, if you have a telescope and you deployed it and looking at something, if someone walks around your telescope and your stand picks up the vibrations of the person who's walking around it, and that will move your telescope off the target you are observing. So you usually want a stand that's as stable as possible, that won't cause interference on your viewing. But we also get 2 different telescopes. Why do we call those telescopes? Instead of radio and visible, in visible telescopes, we have 2 different designs. Yes, refracting and reflecting. That's exactly what I'm looking for. So what are the differences between reflecting and reflecting? Yes, another word for it is refracting and Newtonian. Exactly. One uses mirrors. So which one uses mirrors and how does it work?
So, the refracting telescope, does that one not use just a lens? And yes, does not just use a lens where the lens is where it sort of makes the light concentrated to an eyepiece, and then yes, to the eyepiece, and then the reflecting sort of does the same thing, but then it's reflected to a mirror, to make the image much more concentrated.
Yes, that's exactly it. So when we look at these images, the top telescope is a refracting telescope, and this image below is a reflecting telescope. So here we would have the object we are observing. The lights can be traced to the lens, possibly zoom in. So let's see if I can zoom in. Unfortunately, it looks like I can't zoom in more than this. Let's see if I have something I can. Yes, I can zoom in and I found the controls. Does this help a little bit? So here we have our light rays coming in. Okay, then it only zoomed in for myself. So you can probably, this should be probably a setting you can zoom in. But here we have our lens, and that lens takes the incoming light, that focuses it to where our eyepiece will be, and it will construct the image. In our reflecting telescope, we will have our incoming light rays from the object we are observing. It will hit the mirror. The mirror will bounce it to the eyepiece, where we can construct the image. So what puts the image upright? So in optical telescopes such as this, our image will always be inverted. For space, that doesn't matter to us, because if you look in space, what is up and what is down? So it doesn't make any difference if our picture is upside down in space, because in space there are no up and down. But you can put in correcting lenses that will flip the image the right way around if you are interested in doing such things. Then in image B below, we have focal length. So the focal length is distance from the lens or mirror to the point where parallel rays of light from very distant objects comes to focus. So here we have a long focal length, and here we have short focal length. So short focal length lenses and mirrors must be strongly curved. So for the focal length is an important factor when you're observing certain objects in space, because the focal length will also determine the size of your telescopes. And certain images we want to create looks better through certain kinds of telescopes. So certain images will look better through a long focal length, certain images will look better through a shorter focal length. It all depends on the application and the object we are trying to observe. So these two ways to manipulate light corresponds to two astronomical telescope designs. Refracting telescopes uses a lens, and reflecting telescopes uses a mirror to gather and focus light. The main lens in a refracting telescope is called the primary lens, and the main mirror in a reflecting telescope is called the primary mirror. Both kinds of telescopes form an image that is small, inverted, and difficult to observe directly. So a lens called the eyepiece normally is used to magnify the image and make it convenient to view. Galileo was the first person to systematically record observations of celestial objects using a telescope, beginning almost exactly 400 years ago. In 1610, Galileo's telescope was a refractor. You also learned about the amazing range of Isaac Newton's scientific work. Among his many accomplishments was the invention of the reflecting telescope. So which telescope is more efficient? It comes down to the size of the telescope and which one you are comfortable using. So for example, if you travel a lot and you do amateur stargazing, then using a reflector will be better because you have a smaller focal length and a more compact telescope. But if size is an issue, then you can use a refracting telescope. The distance from a lens or mirror to the image it forms of a distant light source, such as a star, is called the focal length. Short focal length lenses and mirrors must be strongly curved, and long focal length lenses and mirrors are less strongly curved. The surface of lenses and mirrors must be polished to eliminate irregularities larger than the wavelength of light. So in this image here we can see our light coming in, a primary lens. It goes straight through our eyepiece. So here in our reflecting telescope, light comes in, it gets bounced up to a secondary mirror, and then from the secondary mirror down to the eyepiece. So refracting telescopes suffer from a serious optical distortion that limits their usefulness. When light is refracted through glass, shorter wavelength light bends more than larger wavelengths. So for example, blue light, having shorter wavelengths, comes to a focus closer to the lens than does red light. That means if you focus the eyepiece on blue image, the other colors are out of focus, and you see a colored blur around the image. If you focus instead on the red image, all the colors except the red are blurred, and so on. So this color separation is called chromatic aberration. So remember this definition. Telescope designers can grind the telescope lens with two components made of different kinds of glass, and thereby bring two different wavelengths to the same focus. That does improve the image, but these so-called achromatic lenses are not totally free of chromatic aberration. Even though two colors have been brought together, the others are still out of focus. So remember how to fix this. So here is how this is visualized. So here we will have our single lens, and we can see our blue light and red light focuses at two different places. Using a chromatic lens, we can see we can bring these two focus points closer to one another. Telescopes that collect visible light are called optical telescopes. Like visible light, radio waves from celestial objects can penetrate Earth's atmosphere and reach the ground. Astronomers gather radio waves using radio telescopes that resemble giant TV satellite dishes. It is technically very difficult to make a lens that can focus radio waves. So all radio telescopes, including small ones, are reflecting telescopes. The dish is a primary mirror. So do you guys have any questions so far? So when comparing the two, so the image on the left is the Gemini North Optical Telescope in Mauna Kea, Hawaii, and it stands over 19 meters high when pointed straight up. The primary mirror at the bottom is 8.1 meters in diameter. So here we would have a dome opening up, here we would have our mirror. So the sides of a telescope dome can be opened, allowing quick equalization of inside and outside temperatures at sunset, reducing air turbulence and improve seeing. So where is the secondary mirror? So in this image right here, we don't have a secondary mirror in this telescope. So right here where this equipment is, that would be our CCD camera, that will be our spectrometer or device we are using. Speaking about optical telescopes, have you guys thought why those telescopes are inside a dome and why temperature is important? Yes, Mr. Lavuyo.
So is it not because temperature affects things like, for example, the telescope needs to be moved, and so some of the joints are lubricated, and so the oils might drop to a heat where it freezes, and then the telescope will stop functioning, or because the as heat changes material, change volume as well, I think.
Yes, you are completely correct, Mr. Lavuyo, and Mr. Van der Berg and Mr. Visagi, that's also correct. So the dome in a telescope, so what two reasons is: one, to stop distortions of images. But let's think about it. We have our telescope, it's inside a dome, it's sitting in the sun the entire day. So the air inside the dome gets hot, and as the sun sets, the air cools around the telescope. So when you open up the dome, there's a dramatic change in temperature. So with that dramatic change in temperature, you can actually crack this mirror. Or these pieces of the telescope that's metal can stretch and shrink according to temperature. So usually what you do with these telescopes, you have air conditioning systems and heaters inside the dome, and you keep the inside temperature of the dome the exact same temperature as the outside temperature of the dome to stop damaging the telescope, but also to keep disturbances and distortions as small as possible. Then on the right hand side is the world's third largest telescope where I've spent some time, and that is the largest fully steerable radio telescope in the world. So that's true, that's the largest telescope you can move up and down, left and right, spin around 480 degrees. In the world is in the National Radio Astronomy Observatory in Greenbank, West Virginia. The telescope stands higher than the Statue of Liberty and is a reflecting surface of 100 by 110 meters. So this is 110 meters, this is 100 meters, so larger than a rugby field. So how this radio telescope's work is the surface acts like a giant mirror. So we have our incoming rays, and that will be bounced onto our observing equipment called receivers. So question, why don't they just open the windows? Because if you have windows during nighttime, that means you have, could be light sources coming in, and that will cause havoc on our image as well. Yes, Mr. Richard, I have two personal telescopes. I have a 4-inch Celestron, and I have a 11-inch Celestron. Both of them are reflecting telescopes. So, ladies and gentlemen, I think we're going to call it an evening. I see there's 3 minutes left of this lecture. So we will continue on with this lecture on Monday evening. If you have questions, I will remain active for a while still. If you have no questions, have a great week. Good luck with tests if you're writing tests, and I will see you all next week. Then questions, did I capture deep sky images? Yes, my favorite deep sky object to observe from my telescopes is the Orion Nebula. And were they expensive? Yes, unfortunately they were expensive.
So, why are some satellites much more dense? Like why are they made more continuous than others? I don't know if you understand.
Sorry, can you just rephrase the question?
So sir, you get like some telescopes that look like a frame, and I think like they like radio wave telescopes, or maybe they satellites. I don't know if there's a difference.
Oh yes, okay, I see what you mean. So it all depends on the frequency we want to detect. So, for example, the best example usually I give to explain this, if you look at your microwave is sitting at 2.4 gigahertz, the frequency. So when you look at your microwave, you have that mesh grid in front of your microwave that you can see food and you can see whatever you're heating up. So when you have let me get a whiteboard. When we have a mesh grid, this is not nicely drawn, but that will do. And we have gaps in it. And we have an incoming wavelength or incoming wave. And the wave is smaller than these gaps. Then it will go straight through these gaps. So if you look at the microwave, in the microwave's instance, the wavelength of the microscope is bigger than one of these gaps. So for microwaves, because the wavelength is bigger than one of those gaps, the wavelength think it's a solid surface, if I can phrase it that way. So it gets reflected off the surface because it's too big to pass through the gap. So when looking at your telescopes, if it has a mesh surface, it's usually looking at larger radio waves that you can reflect off it. But if you have smaller waves, it can pass right through it. So it all again depends on your application, if that answers your question, Mr. Levuyo.
That's a nice fact, sir. Thank you.
Pleasure. So, question. Why would you save for a car if you could save for a telescope? Good question. So why save up for a telescope when you could save up to launch your Tesla into space? Very good. There are some good telescopes, unfortunately, cost the same price as a small car. So I'm going to stop this recording. You're more than welcome to log off. If you have more questions, I will be available for another minute. Otherwise, have a great evening, great week, and I'll see you all next week.